In this video, we're going to look at one of the two nuclear processes that emit or give off a huge amount of energy. One is nuclear fission, which we're going to talk about now, and the second one is nuclear fusion, which is in a separate video. So the word fission is not just used in nuclear science. Fission means to split or break apart. Whoops. So in nuclear fission, what we're doing is we're splitting heavy nuclei, so larger nucleuses, into lighter ones, and look what else they're going to make, neutrons. And the symbol for a neutron in nuclear reactions is a 1 on top, a 0 on the bottom, and the lowercase n. So if you see a 1, 0, n, that's the symbol for a neutron. Now on the last page, we'll talk more about this, but nuclear fission reactions are the source of energy in nuclear power plants. Okay, so you can see right here, source of energy in nuclear power plants. Well, let's look at the equation, this nuclear fission equation, because it does have a few differences than the nuclear equations that we wrote in previous videos. So let's take a look at it right here. So what happens is we have a large nuclei here. This is uranium-235. And so there's my large nucleus, and it is bombarded, just hit with a neutron. And so how that's written in the equation is they put plus because they're hitting the uranium with the neutron. So that's what's happening on the reactant side. Then we have the arrow, and what it does, remember, fission splits apart a heavy nucleus, uranium-235 in this example, making smaller nuclei. And so we have smaller nuclei on the product side. We have, this is what, krypton 91 and barium 142 plus 3, so there's a coefficient, but it means 3 neutrons. Now, the production of the neutrons here is significant because we need neutrons as a reactant. So these reactions, if left uncontrolled, can have or are a chain reaction. So, and your book has probably a better illustration than I can draw. But let's say I start with 1 uranium. Here's my little dot down here, my red dot for my uranium. And it goes out, it produces 3 neutrons. So 1, 2, 3. So now those 3 neutrons in the sample can react with 3 more uraniums, my little red dots. My drawing doesn't like it when I do circles. It wants to move the page around. Okay, so then each one of these would produce 3 more neutrons. So we go from reacting with 1 uranium. Let me see if I can just make it thicker so that I don't have to try to draw little circles. Okay, let's try. There we go. So now it goes to 9, and it would just keep going. So left uncontrolled, this It's a chain reaction, and if you have a critical mass of uranium not controlled, it can lead to an explosion, because each time this reaction happens, we get lots of energy. All right. So that's the significance of making 3 neutrons in the back as a product. So you can see, it says the released neutrons can then bombard, hit other uranium, creating a chain reaction, and that could keep going. The critical mass is the minimum amount needed to sustain that chain reaction. So if it was lower than that, you wouldn't sustain it. In nuclear power plants, they use a boron rod, boron the element. And they absorb the neutrons. And so then they can control how much is going forward because it's absorbed by the boron rod, or less would be absorbed. And so they can control it. So that's a nuclear fission reaction. So we're going to do 2 things. We're going to look at a nuclear fission reaction and see if we can put one together. And then we're also going to look at a few more details about the nuclear power plant and some of the pros and cons. So this is our question. We're going to try to write a fission reaction. So it says, write the nuclear reaction for the fission of uranium-235, okay, by a neutron bombardment. Okay, let's get that part. So uranium is U-235. Now I have a periodic table in the slide, so let me go. Now, some of these in this chapter, you might have to look around a little because we're not used to using them, but uranium is way down here in the inner transition metals. It's element 92. So put the 92 here, and then it's being bombarded with neutrons. Okay, so that's the first part. Then it says to form, and so let's see what our products are. It forms antimony 133, 3 neutrons, and then 1 other isotope. So remember, in a fission reaction, we form smaller nuclei and more neutrons here. So let's get the antimony, so 133. Now antimony may be also another one that you don't know the symbol for. But if you look, so this one's not in the bottom. Antimony is right here, number 51. It could be a little bit of trickery if you were looking for it the first time, because its symbol, SB, doesn't look like its name. So, but it's SB and it's number 51. So there's our antimony, plus 3 more neutrons. So 3, it says there's 3 right there. Neutrons, and then 1 other isotope, so we need to figure that one out. Now we're going to use the things that we've done previously to figure them out. So we have to have the sum of the mass numbers equal on both sides and the sum of the atomic numbers equal on both sides. So on the reactant side, 235 plus 1 is 236. Then we come over to the product side. We have 133. Now, since we have a 3 here, that's like a coefficient, so it has to multiply through. So 3 times 1, so there's 3 on the top. So 133 plus 3 is 136, plus something I don't know. Okay, so if we look on the reactant side, it's 236. On the product side, it's 136 plus some number, so that number has to be 100, right? Because 100 plus 136 is 236. So the top number is going to be 100. All right, then let's do the bottom. So it's 92 plus 0, that's 92. Then I have 51 on the antimony, But here's a 3, but it's 3 times 0, so this is still going to be 0. So 51 plus 0, that's still 51, plus some unknown number I don't know. So 92. So let's see. So 92, 51 plus what? 41? So 41 plus 51 equals 92. Yep. So that means our bottom number is 41. So let's go to our periodic table. And we're going to find element 41. So where are we? Niobium, right there. So we'll go back. So it has 41, and it's niobium. So this right here is the nuclear equation that they have described. So remember, and this is the first time in a nuclear equation, one, we've seen two things on the reactant side, but we treat it the same way, just add it up. And then the second thing is when you have a coefficient, remember to multiply through both the mass number and the atomic number when you're trying to figure out what the numbers are when you have a coefficient. So let's look at a few things to round out our overview of nuclear fission. So the first sentence is already something that I've mentioned, that this is the type of nuclear reaction that is used in a nuclear power plant. And these reactions give off a large amount of energy. In fact, it is, if you compare it to something like coal, which is another source of energy in electrical power plants, it's 8,000 times more efficient. So this is an advantage to nuclear reactions for power plants because they are very efficient at producing energy. Now your textbook has an illustration, but I did want to just point out in this second bullet point that when we talk about generating electricity, it is a process where different forms of energy are transferred into and transformed into other forms of energy. So we start with a source energy, and in this case it could be nuclear power. That nuclear power boils water, then that water creates steam, which runs a turbine, and turbines create the electricity that then goes out. You could use different sources at the original point. So like you could use coal. You could have coal, which is burning of coal. That's a chemical reaction. But then the other process would be similar. You'd heat water, boil it, it creates steam and generates electricity. Or you could use natural gas, which is also a chemical reaction. And it would do the same thing. It boils water to run the turbines to generate electricity. So people are weighing the advantages and disadvantages of that original energy source. So even when it's talking about this type of power plant. So an advantage to nuclear power is it's very efficient, right? Very efficient. Things you have to consider, there's a couple things. One is the radiation possibility of leaks or accidents. And two, which I think is a big one, is how do you get rid of the waste? Because some of the products generated in the nuclear reaction are also radioactive. And a lot of the chemicals have very long half-lives. So that really is something that's a major consideration. They can minimize radiation leaks by having, like you see here, containment facilities, investing in good infrastructure, maintenance, training of workers. So there's a lot they can do to prevent the types of things like radiation leaks. Nuclear waste is a different kind of problem. Currently, they bury it. But you have to have places willing to bury nuclear waste. And is that the best thing to do? Do people have to take care of it for a long amount of time, longer than we'll be alive? I mean, you saw some of the half-lives. So how you treat nuclear waste is a big problem. Decades ago, states would accept money to bury the waste as part of their budget. Companies, the government would pay them and they would bury it. But, after a while, people didn't like that so much, so I don't think it's as popular. Nobody wants it buried near where they live, understandably. So nuclear power is very efficient, but it does have some obstacles that it has to overcome. In Europe, I was reading one place where they actually start to recycle some of their nuclear waste. And by that, I mean they reuse it. So that could be an option where you wouldn't have to bury it, but you could reuse it for other things. So as far as nuclear fission goes, just to recap, I want you to know the definition. I want you to be able to know that it's the energy used for nuclear power, that it can form a chain reaction, meaning that it can self-sustain itself. You can know it's efficient. You could, as a pro, maybe the radiation leaks and the nuclear waste as a con. Just know it gives a large amount of energy. Also be able to complete a nuclear equation similar to the one we did in this example.